This is a revision lesson covering p10 and 11 and a summary of the photoelectric effect. So first of all, we started off by showing you an electroscope. The electroscope is something similar to the one in this picture. So you've got a metal cap at the top and joined to a rod with a leaf, it's called, that can stick out. So if you arrange to have a surplus of electrons on the electroscope, they will repel each other and spread out down the leaf. And because you've got electrons on the leaf and on the rod, they'll repel each other and the leaf sticks out. And then it was found that if you shone light on the cap, under some circumstances, that would cause the leaf to fall. Now, what's going on there? It can only mean that some of the electrons are escaping from the metal. Now, the whole system is isolated, so they can't leak through the case. They must actually be jumping off the metal and into the air. But they also found that it only happened if the light had a high enough frequency. So low frequency light, nothing happened. But if the light was a high frequency, then the leaf did fall and the electrons did escape. So a few more experiments, and they found that as the frequency increased, the electrons that escaped had more kinetic energy. They also found that as the intensity increased, you get more electrons, but they had the same average kinetic energy, so they weren't any more energetic just because the light was brighter. They also found that below a certain frequency, you got no electrons at all, no matter how bright the light. Now, if light is a wave, a nice smooth thing that the electrons could receive and sort of save up until they had enough energy to escape, none of these things would be true. So there had to be a different explanation for what's going on. So the conclusion was that the light is actually arriving in lumps of energy, and we call those lumps photons. So the higher the frequency, the more energetic the photon. So there's a relationship between energy and frequency, which is E equals HF. So E is a constant times the frequency, and the constant is called Planck's constant, 6.63 times 10 to the minus 34 joule seconds. That's not a number you need to remember, it is on the formula sheet. But it's a directly proportional relationship. Energy depends only on the frequency of the photon. So, an electron can only escape from a metal if it gets enough energy from a single photon. So the idea is that it's a bit like if you imagine a coconut shy. It wouldn't matter how many ping pong balls you threw at the coconuts couldn't save up all that energy from the ping pong balls until they've got enough to fall off their stand. They've got to have the energy arriving in one lump. So in this diagram, if we've got a 700 nanometer photon, it has 1.77 electron volts of energy, but this metal, potassium, needs 2 electron volts for the electron to escape. So this photon isn't energetic enough, and you wouldn't see any electrons coming out. This one is 550 nanometers, and therefore has 2.25 electron volts. And that's enough to escape, plus a bit left over, the 0.25, to give it some kinetic energy. Off it goes. An even more energetic photon, a mauve one, 400 nanometers, 3.1 EV, that's 2 to escape, plus 1.1 to turn into kinetic energy. So that would escape faster. That's the general idea. If you plot the kinetic energy of the escaping electrons against the frequency of the photons, you get this graph. The equation for the graph is y equals mx plus c, so kinetic energy is hf minus phi. I've written it the other way around here. Hf is phi plus ek max. I think maybe that's easiest to see where it comes from. So the HF is the incoming photon, that's the energy arriving. That provides the energy to free the electron from the metal, that's the phi, and phi is called the work function. And any spare energy left over becomes the kinetic energy of the free electron. So that sort of does it in sequence. As I say, the equation for the graph is just written the other way around with kinetic energy as the subject. So if the threshold frequency is met, so if the energy, the frequency of the photon is enough, that will just allow the electron to escape, but there won't be anything left over for it to have a kinetic energy. So that frequency is called the threshold frequency, and it's sometimes called F0. Below that frequency, the energy is not enough to let any electrons escape, so you get none free. And in fact, this is the work function. This is the minimum amount of energy you need to supply to free the electron in the first place. And different metals have different work functions and different threshold frequencies. So in this diagram, it doesn't show you the phi's, the work functions, but if you can imagine extrapolating these lines down until they hit the y-axis, you would see that each one would be hit at a different distance below the axis. So they've all got different work functions. So cesium only needs a small amount of energy for the electrons to escape. Calcium, the mauve line, needs a bit more, that much. Mercury would hit right down off the screen, so that would need a lot of energy to allow electrons to escape. The key other thing to notice is that they have the same gradient, which is Planck's constant. So they're all parallel lines. So from these graphs, you can get both the threshold frequency with this intercept and the work function by the intercept on the y-axis.